Thanks for taking a little time out of your day to join us here at Hawk Ridge Systems for another webinar. Today we're talking multi-physics. Well, let's do some introductions here. So my name is Tim Newton and I'm going to be kind of acting as the host, but Terrence Wu is going to be doing the hard work. Terrence is one of our product managers and he's in charge of the Simulia Abacus product line. So that's some high-end simulation capabilities that sometimes involve multi-physics. So he's a real subject matter expert for us. Now, Terrence came to us, you've been with us about 8 years now. He started off in an application engineering role where he did things like demonstrations, creating training and content for a YouTube channel, as well as consulting. And while he was an application engineer, he got a lot of exposure to the SolidWorks simulation product line, which was really a great primer for him to move up and into Simulia Abacus. So Terrence, can we hear you?
Absolutely. Well, I don't know. Hopefully, can you hear me?
I got you loud and clear. You're good.
All right. Thanks for the lovely intro there.
So, here at Hawk Ridge Systems, quick commercial for those of you who are new to us. At Hawk Ridge Systems, we deal with engineering, design, and manufacturing, both software as well as hardware, to make that as easy as possible. We also have the training and services to back that up. It's our vision to bring product realization solutions to radically improve the way you bring your products to market. So today we're going to be focusing kind of on the upper right-hand corner there, talking about what's possible with SolidWorks simulation, Simulia Abacus, and some of the other tools in that simulation space. So Terrence, I think you've got an agenda for us. Why don't you go ahead and show us that, and we'll be off and running.
Absolutely. All right. Thanks, Tim. And of course, that is the topic for today, is multi-physics simulation. So we're going to go through and do an overview of that. It is a very big, very broad topic, so we won't be able to get into too nitty-gritty of detail, but I'm hoping to go through a good number of examples of common types of multi-physics simulation. So there's some that we hear about more often than the others. They come up over and over again, and I'm hoping to make sure you guys are familiar with those and make sure you know sort of what the framework for those is and how to use them. As we go through, we're going to define some terminology. There's a lot of jargon when people start talking about these more complicated analyses. Not everybody even agrees on what those terms should be, so hopefully you can clear up some of that. Probably going to make it a little muddier in some areas, but we'll do our best to make that clear. We also want to know, when do we need multiphysics simulation? Multiphysics is a great thing and can really help us out, but it's not useful all the time. So we want to make sure you guys understand when you need it, when you don't, when can you keep things simple, and when do you need to make them a little more complicated. And then, of course, there's a lot of different ways that we can tackle these problems. So we want to understand the different options that are available to us, and also the different tools that you can use to use those techniques. So half of you are using simulation today, and we usually have some sort of goal when we're conducting a simulation. There's a lot of different reasons that people will throw out, but it usually boils down to one primary goal, and that's to predict how something is going to work, how it's going to perform. And we're going to take that information and usually try to make some sort of decision, whether that's to improve the product, make sure it works, maybe we can keep it working but reduce the cost. There's some sort of benefit to doing this, but at the root, we're still just trying to predict how things are going to work. And there's a number of different types of simulation that we do to make these decisions. Some of the more common ones, or the ones that we're going to talk about today, are, of course, stress analysis. You might be interested in the dynamics of a system. You might want to look at fluid flow. Maybe need to take a look at some thermal analysis, look at some electromagnetics. And of course, there's lots of others. Some people want to simulate chemical reactions or things like that. Now, we just defined why we use simulation. It's to provide some sort of decision benefit, some sort of information that we can go and make decisions with. And if we want to make good decisions, we need to be able to predict that performance, but we need to do it accurately. It's very important, otherwise we're going to make bad decisions based on bad information. So why do we use multiphysics simulation? Well, it's the same route to goal. We're trying to predict performance using physics calculations, but we're going to be considering multiple types of physics. And that's important when we have problems where you need multiple types of physics to get an accurate result. Right? Some problems can be described with one type of simulation, but some problems, if you try to use only one type of simulation, you're going to get a bad result. And so it's those examples where we need to look to a multiphysics solution, and identifying that and knowing how to use that actually takes a little bit of work. There are some questions that you need to be able to answer. The first of which
Terrence?
is, yes, Tim.
Sorry to interrupt. I was looking in the question area. There's a whole bunch of responses from the audience about the multiphysics. So heat transfer, stress and vibration, dynamic stress and strain, heat transfer, electromagnetics and fluid flow, and one more on stress, CFD, Joule analysis, and heat transfer. And I got a preview of this, so I think the audience is in good shape. You've got quite a bit of this covered.
Awesome. Yeah, that's fantastic. I was trying to keep my eye on that window, but I missed it. I was looking in the wrong box there. I was looking in the chat box. So that's
No,
awesome.
thanks for everybody for participating. We love it.
Yeah, really appreciate that. I was worried you were all not hearing me there, but great to see these coming in. And yeah, I think we've got a lot of great content to address these exact topics. That's awesome. So yeah, back to the questions that you need to be able to answer in order to conduct a multiphysics simulation. The first is, what physics are relevant? The world we live in is inherently multiphysics. Unless you're solving a problem in a vacuum, there's going to be some fluid flow. Unless everything's at absolute zero, there's going to be some heat transfer. But sometimes it's not important to simulate these factors depending on what you're trying to learn about. If I'm trying to do a drop test, maybe I'm taking my cell phone and dropping it on the ground, it's going to encounter some air resistance as it moves down to the floor, but it's probably not enough that I care to add that in and do a fluid simulation for that drop test. So we need to be able to make these decisions on what is important to the study at hand, and then that'll pretty easily lead us into the types of simulations that are going to need to be included. So for the drop test, it's going to be dynamic, stress and strain. Yes, Tim, sorry.
I was just going to dovetail on that. I've always thought it's interesting how in simulation in software we can separate our physics and find out what's important. Sometimes as engineers, we tend to overcomplicate things at moments. But in simulation, I take this crawl, walk, run approach where I can start by adding physics by physics to understand what's really driving the problem. I had a heat transfer one a long time ago that we thought radiation was really influential. And then by separating out the different heat transfer mechanisms, we actually found out that really wasn't a very viable cooling approach. And we had to look at some of the other heat transfer and convection in that case.
Yeah, that's a great point. You absolutely start to learn which parts of the simulation are important, which types are a bigger player in that particular problem. When we look at the different types of simulations that we're trying to put together, we do need to know whether they're independent of each other or whether they're interacting. And when they do interact, how do they interact? This is going to lead us into whether we can conduct an uncoupled or a coupled simulation. And we'll get a little deeper on that topic later on in the presentation. The next question really links with what you just said, Tim, which is that you need to know which type of simulation is important for the problem. If you've determined that you have a thermal structural analysis, sometimes you're more concerned about the thermal part, and sometimes you're more concerned about the structural part. And you need to be able to identify which case that is, because it's going to lead you into which technique you're going to use. All right, some techniques are going to get you a better structural result, some are going to get you a better thermal result, and it's also going to allow you to choose the right software tool for the problem. Now, a little bit on software. We've got a pretty wide portfolio here at Hawkridge Systems. We have some tools from SolidWorks. We have some tools from Dassault Systems, the parent company of SolidWorks, and their Simulia brand. I'm going to briefly mention the programs that were used for the examples here today, but I want to remind everyone that the focus here today is on the techniques. The software is secondary to the approach. You want to pick the right approach for the problem and then choose the software that'll let you use the correct approach. So we'll mention these here. We've got, of course, SolidWorks Simulation, which is our FEA tool built directly into SolidWorks. Works really well for fast, quick analyses in the design process, and it can also handle some pretty complex problems as well. Got SolidWorks Flow Simulation, which is our computational fluid dynamics tool inside of SolidWorks. We've got some examples using the Simulia Abacus tool. Like Tim mentioned, this is where I spend a lot of my time these days. This is an analyst level tool, so it's quite a bit more complex, got quite a bit more capability. And so when you get to really challenging problems, this can be a nice option to turn to. We're going to see some examples using Simulia CST Studio Suite, which is an electromagnetics simulation tool. And we're also going to see a little bit of Simulia XFlow, which is another computational fluid dynamics tool using a different type of technology than the SolidWorks Flow Simulation tool.
Hey, Terrence, what kind of problems would you point XFlow at versus SolidWorks Flow?
Yeah, that's a great question. We'll dive in a bit deeper, but as a brief overview, XFlow is really good for highly transient, turbulent flow situations. It uses a technique called lattice Boltzmann. It's a newer technology, and it works really well for those situations. Flow simulation, on the other hand, uses the old Navier-Stokes set of equations, but it's got a bunch of really good capabilities for solving thermal problems, which XFlow can't do.
Thanks.
Yeah. You'll notice in blue here that we've got some solvers listed out. Analysts like to talk about programs, but they also sometimes talk about solvers. Some programs have multiple solvers built in, and these solvers can achieve different things. And some programs like flow simulation just have the one flow simulation solver. The key here is just not to get tripped up when somebody says a solver. Sometimes they mean program, sometimes they mean a particular solver in the program. These terms get thrown around pretty interchangeably. So let's get into some examples here. The first broad category of examples that I want to look at are fluid structure interaction problems. And I'm going to start off with an example that isn't really fluid structure interaction. We're going to look at this pressure vessel here. I've got this pressure vessel and I want to apply an internal pressure. And so there's some sort of fluid inside, it's pressurized at 165 PSI. It's going to exert a force on the structure. And so we have a fluid interacting with the structure. Sounds like fluid structure interaction to me. But in the multiphysics world, most people would not consider this an FSI simulation. And the reason is we don't actually need to do a fluid flow analysis. If we've got a constant uniform pressure on the inside walls of this tank, we can just go and apply that as a pressure to the internal surfaces in a stress analysis. And so we really only need to do one type of simulation. So this is a great example of where something can appear to be multiphysics, and in the real world, it is. But in the simulation world, we can tackle it with one type of simulation and keep things simple. And I don't know about you guys, but anytime I can keep things simple, I like to. So if that's not fluid structure interaction, what is? Well, here's a good example. If any of you have taken our flow simulation training course, you might recognize this model. We've got a billboard and it's going to get some wind loading. Unlike that tank, we don't have a constant force across the entire billboard face. We're going to have areas where there's higher velocity and lower velocity, low pressure, and high pressure. And so we actually need to model that fluid if we want to get a good result. We can run the fluid simulation in a CFD tool, and then we can take the results, use the fluid pressure and shear forces on the faces of that billboard structure, and put that in as the input for our stress analysis. We'll be able to see how much that wind makes the billboard flex, what the deformation is, how much stress there is, make sure nothing's going to break, maybe remove some material, and we've got a fluid structure interaction simulation using 2 different pieces of software. Key distinction to make here is that this is what we call an uncoupled fluid structure interaction, or an uncoupled multiphysics simulation. And uncoupled is in contrast to coupled. Now, these are a couple terms that get misused or used differently quite a bit. I've heard some people call uncoupled simulation loosely coupled. I really hate that because it sounds like the opposite. Or sometimes it's called sequential. I actually like that a lot because that describes pretty accurately how we do things, right? We do the flow simulation first and then the structural simulation after in sequence.
I agree, Terrence. I think that's the best way to describe it as a sequential thing. It's solving the deformation on the billboard and then solving the pressure distribution on the billboard and then solving the displacement. If you've ever watched a billboard dance in the wind, that's maybe something called aeroelastic flutter. And that's a dynamic problem where the pressure on the billboard causes deflection, which then changes the pressure distribution and changes the deflection. There you would need that coupled, and maybe that sequential isn't the right approach for the flutter kind of thing. Does that make sense to you, Terrence?
Yeah, that's absolutely right, and exactly where I was going with this slide. So that's perfect, Tim. That's a great example. Right, uncoupled is going to work really well when there's a one-way push of information. So if you have the flow on the billboard and it deflects the billboard a small amount, but it's small enough that it doesn't change the airflow patterns around the billboard, then uncoupled is going to work well. But if you've got some sort of behavior where the billboard moving is changing the flow, that's a two-way interaction, and that's when you need to do a coupled analysis, where you're simulating the fluid and the structure at the same time. And so sometimes coupled analyses get called as simultaneous coupled analysis, tightly coupled or fully coupled, but all of those refer to that type of problem where you've got the structure influencing the flow as well. We looked at an uncoupled problem. Here's a coupled fluid structure interaction. We've got a tire and it's rolling through some material. We're using a technique here called coupled Eulerian Lagrangian, which is a bit of a mouthful. The Eulerian term refers to the type of mesh that's used for the fluid. Eulerian mesh works really well for things with a lot of deformation. So fluids like the water, you can see there that the tire is running through in that hydroplaning analysis. Or on the right, we can also use it for things that aren't fluid. We've got a soil example there, so we can see the tire interacting with a material that's deforming a lot, but isn't quite a liquid or a gas. The Lagrangian term refers to just regular meshed parts that we're used to. That's a Lagrangian part. And we couple them together by modeling the contact between the fluid and the solid. We're using Simulia Abacus for this example here, and so that's done with general contact in the Abacus explicit solver. You can see we've got the flexible tire, and so we end up with a nice plot of the contact pressure out of this analysis. Another example here, this one's a little more dynamic. We've got a tank full of water. The tank, the supports, and the impacting object are all using that Lagrangian modeling, but we have that Eulerian liquid inside. Same technique here. Got a tank and the baffles model is Lagrangian, and you can use both regular solid elements or shell elements for thin-walled things, and we can see how that water sloshes. Now, this CEL technique can be used for gas problems as well, so that Eulerium can be used there. We've got this explosion inside of a gun barrel. And so for this, we're using it to represent an ideal gas, and we're inflating that gas to get that explosive behavior and see the stress on the structure. It's important to note here that this is just a fluid structure interaction. We're not modeling the chemical reaction of the explosion, right? That would be adding in yet another type of physics to the problem. Not important for this one here, but I'm sure there are times where you would want to include that behavior. And then another air problem, pretty similar, but this one's using a more flexible structure. We're looking at this airbag inflating. Okay, so this is the CEL technique, and it's one of the most common approaches for fluid structure interaction problems. When a fluid structure interaction or an FSI problem comes up, it's usually one of the first methods that you want to consider. Another really common method, though, is something called smooth particle hydrodynamics, or SPH. In the Eulerian method, we have a mesh and we have the material moving through it. In the SPH technique, this is a meshless technique. Instead, we have a series of points where we're going to be solving for that highly deformable or fluid material. Because it's meshless, it works really well for some types of problems and can be a lot more efficient than the CEL technique. Most of the problems that you can solve with CEL and SPH can be solved with either way, and the method that you choose is going to be based more on the particular problem than the type of fluid or structure or anything like that. In this example here, we've got a bird strike where we've got our solid engine blade doing a real poor number on our fluid bird. I'm a little sad for the bird being represented as a fluid, but the blade's not doing so well either. You can see it deforming there as it makes impact. All right, so we've got this represented as a series of points. Strictly speaking, they're not actually particles, but it's pretty handy to think of them as particles, and that's why this technique gets the smooth particle name. Another SPH example here is this CV joint. We're seeing where the grease inside the joint is going to move as it starts spinning and how that rubber boot is going to expand and deform. Now, both the CEL and SPH techniques are really good at doing FSI when the structure is the most important part of the problem. However, if the fluid is the more important part of the problem, you've got some really interesting fluid behavior, sometimes the accuracy of CEL and SPH isn't enough. And that's where you need to turn to a true computational fluid dynamics approach rather than one of these finite element analysis approaches. This example here, we've got something that's really, really turbulent. And as we mentioned before, XFlow is a really good tool for that. Right? It uses lattice-Boltzmann CFD. And so it works well for these transient situations with really dynamic flow. And built into XFlow, you can also include the rigid body dynamics. Those of you that might be using SOLIDWORKS flow simulation right now will know that that's a limitation of that software, is you can't have moving geometry. And so here we can see how the fluid interacts with a moving piece of solid geometry, and we've got that structural interaction, and it's all done within the XFlow tool. And so this is a case where the fluid is more important than the structure to us. So sometimes the fluid's more important, sometimes the structure is more important. What if they're both really, really important and you want to be able to model them both super accurately? That's when things start to get pretty complicated, and we have to start to think about cosimulation. So this is a term that comes up in a number of different ways. Cosimulation is any time you're using multiple solvers to simulate a problem. We looked at a billboard example where we took flow simulation results and moved those into SOLIDWORKS simulation. Some people would consider that co-simulation. Most people wouldn't, though. Usually co-simulation implies that you're doing a simultaneous coupling of the two solvers. And so if you're doing that, the solvers are going to need to exchange data, not just hand off results from one to the other, but back and forth. So every time step, you're going to pass information from the fluid to the structure, and you're going to pass information from the structural analysis back to the fluid analysis. Co-simulation refers to any time you use multiple solvers, whether those are in the same software package or whether they're solvers from two different programs.
That aeroelastic example I talked about earlier, Terrence, that would be one, a case for co-simulation where you just have to have the CFD, the pressure distributions, coupled to the structural in order to see that dynamic behavior.
Absolutely, yeah, that would be very similar to the example that we're looking at on screen now with this parachute, where you've got something happening really active with the fluid, and so you need that good, accurate CFD analysis, but you've got the structure deflecting, and you need to be able to see that deformation. You know, a rigid structure just won't do. And so for this parachute here, you know, we're coupling abacus and xflow together. Every time step, xflow is handing the flow pressures data over to abacus, and abacus is calculating the new deformation of the parachute and then handing that new shape back to xflow in order to recalculate the flow distribution. And so that's happening back and forth all throughout the simulation, and we've got a true coupled co-simulation between CFD and FEA. So we're going to change gears a bit here and hop into talking about some thermal structural analysis. So thermal structural analysis, another really common type of multiphysics problem. First example I want to look at here, kind of like when we started talking about the fluid structure interaction, is not really thermal structural. We've got that pressure vessel again. This time we're heating it up. Everything's going to be at 700 degrees Fahrenheit. And of course, that's going to cause some thermal expansion. There's going to be stress resulted from that. However, because everything's at a constant temperature, I don't need to do a thermal simulation. I can just apply that temperature in the stress analysis. So again, a case where we can keep things simple. We only need one type of simulation. It's not really a multiphysics simulation, even though we are taking into account the physics of temperature. Of course, if we don't have everything at a constant temperature, then we will need to do a thermal analysis. A lot of you may know that there are two main approaches in simulation for taking care of a thermal problem. One is to use an FEA tool, and the other is to use a fluid analysis tool. Typically, for the thermal side of things, the fluid tool is going to do a better job anytime convection is involved. In the FEA approach, only solid geometry can be analyzed. We can't actually model the fluid. And so we're guessing or representing with some pretty big assumptions what that convection is going to look like on the surface with a convection heat transfer coefficient. If convection isn't a large part of the heat transfer, then this can be very accurate. But if you do have a lot of airflow, if that, whether it's natural convection or you've got a big fan pointing at something, then you really do want to turn to a thermal CFD solution. And the thermal CFD solution is, strictly speaking, multi-physics. Even though we can do this all within one tool in SOLIDWORKS flow simulation, we are looking at heat transfer and fluid flow at the same time. You may have heard the term conjugate heat transfer. It's referring to having those multiple types of heat transfer analyzed at the same time.
Good point, Terrence. That comes up often, conjugate heat transfer, and that's just something that we do in, well, you can actually, and flow simulation. Sometimes maybe just a point of clarity for folks, they want to know, why would I do thermal and flow versus structural? I think, in my opinion, it's all about modeling convection versus placing convective film coefficients to try to replicate or approximate a complex phenomenon like
Yeah, and that's exactly right. Anytime convection is not very easily defined, that flow simulation tool is going to do a much better job for you. As we start to think about linking that with structural, though, there's a couple ways we can do that. We can do it in the sequential or uncoupled method, or we can do a fully coupled analysis. This expansion joint example, we've got something hot running through the joint, and it's going to heat up the inside of the joint. The outside, though, is not as hot. And so we've got a temperature gradient through. So we need to do that thermal analysis. Depending on the conditions and how well we know what's happening, we could do that as a FEA analysis or as a CFD fluid analysis to get that temperature on the left there. And then we're going to take that gradient, doesn't matter which way we got it, we're going to go and we're going to do a stress analysis to figure out the structural portion of it. Again, just like the billboard, it's a one-way transfer of data. We're making the assumption here that the joint, because of thermal expansion, is not going to change shape enough to change how the thermal behavior happens as this thing heats up. So we're not significantly changing the shape and the heat flow through the part. On the flip side, if you are significantly changing the shape and it's happening at the same time as the heat transfer, then you need to turn to a fully coupled analysis. Right, so for this hot forging example, we've got the thing turning into a totally different shape. At the same time, we've got that heat transfer. There's no way that we could do this as a one-way transfer of information. We need to handle these both at the same time. And so we're taking care of that in one coupled analysis, and this one is built into Abacus. Next up, let's talk about thermal electrical. So when we talk about linking thermal and electrical, we're usually referring to Joule heating, right? As a current passes through some piece of geometry, the resistivity of the geometry is going to create some electrical losses, which will heat up the part. The trick here is it usually needs to be coupled together because as the part heats up, the electrical conductivity or the resistivity is dependent on the temperature. And so that's going to change how the electrical current moves through the part. So we need to look at them both simultaneously. Needs to be done as a fully coupled Joule heating problem. And this can be done in Abacus if you're looking for an FEA approach, or it can be done in flow simulation if you have some convection to consider as well. We can also take a look at heating as a result of electrical current due to induction heating, so electromagnetism. In this example, we've got this gear and we're heat treating it with induction. This particular problem wanted to look at what happens if you use multiple frequencies. The different frequencies are going to give us a different skin depth on that heat treatment, allow us to get faster heat treatment and more consistent. And so we need to look at the eddy currents due to the electromagnetic behavior. We need to look at the Joule heating, and we need to look at the thermal profile as it heats up all at the same time. So again, fully coupled. This one can be done in Abacus, or it could be done in CST. They both have a portion of the solving power. Abacus is going to be your choice if you're more concerned about the structural part, and CST is going to be your choice if you're more concerned about the electromagnetic part, or you might be driven to one or the other based on what you have available to you at the time. And of course, as you heat things up, we had thermal structural, we have thermal electric. Why can't we have all of it? Thermal, electromagnetic, structural. We've got this frequency filter example here. We had a pretty high power input, and that high power is going to cause it to heat up. So we need to do an electromagnetic calculation. You can see a little F there in the green box. You may have noticed when we had the slide with all the programs and solvers on it that the CST Studio Suite program had a lot of solvers listed out. So this is a 4 simulation, 3 solver workflow, all inside of CST. We're using the frequency domain solver to solve the electromagnetic problem. We're taking that information and using the thermal solver to figure out the heat. Then we're taking that and feeding that into the structural solver to figure out what the deformation is going to look like due to thermal expansion. And then because of the shape change, we have to go back and do another electromagnetic analysis to figure out what the filter response is going to be. And this one, we actually saw that as it heats up, the frequency is going to shift down just a little bit. And so it's important to incorporate all of those.
Terrence.
Yes, Tim.
What we're looking at here is very close to a question that's just come in from Dennis. Actually, a moment ago, but it was probably when you had the Joule heating example up. And his question is, Joule analysis of a structure that deforms due to asymmetrical heating, that changes the contact surfaces that change, then in turn change contact resistance between components. What might be the best combination of solvers? And not that we're prescribing a solution here, but could you just, did you follow that? So thermal distribution that changes contact, probably areas and resistances, what would that look like?
Yeah, I would say that if you're expecting a pretty good amount of deformation and it's all happening within a solid structure, that you're probably going to want to lean towards the abacus workflow. That's going to allow us to solve the structural problem best. And when you have large deformations, that's usually the trickiest part of the problem. Although, of course, there's some capability for that here in CST as well. Or we could start looking at, doing some of the problem in flow simulation and moving to SolidWorks simulation. It does depend a little bit on the interactions, and we do need to, I probably need to know a little more about the problem, but on the surface, I'm expecting that the deformation is happening and changing that, electrical path through the part, and so the abacus workflow is probably going to be the best.
Right. So in abacus, the thermal and structural, so that they co-simulate.
Exactly. Okay. So we've gone through a number of different examples, and they've ranged in complexity from very, very simple to very, very complex. The complex problems are challenging because you need to know a little bit more about the problem and have a lot more inputs in order to properly define it. But the other part that's really challenging is big problems take a long time to solve and require a lot of computational power. Something we're seeing a little more of now, and those of you in this webinar have probably seen marketing around this, that this new 3D Experience Simulia set of tools, or Simulia Works set of tools, they've branded it a couple of different ways, is available, and it uses a lot of the Simulia technology that we've seen in the traditional desktop programs, but it puts it on the 3D Experience cloud platform. One of the biggest benefits that I see with the cloud is that we can take advantage of cloud compute. So rather than solving the problems on our local machines, having to buy really nice processors and graphics card, we can solve it on the cloud using Dassault Systems machines. And I don't need super fancy hardware. I can use their power to handle my large problems. And so that brings me to the end of the topics that I had planned out for today.
Thanks to everybody for joining, and we'll look for you on the next one. And thanks, Terrence, for presenting. It was very interesting.
Awesome. Yeah. Thanks very much for riding along, Tim, and helping with those questions. And thanks everyone again.
Okay. Thank you all.